The James Webb Space Telescope is revealing the universe like never before. Our planets, the furthest galaxies, and the strangest phenomena.
And what you can see is actually material falling into a black hole.
And that's only in the first few weeks. There's going to be a lot more discoveries to come.
The James Webb Space Telescope is a product of decades of hard work from scientists around the world.
I have been waiting my entire astronomy career for JWST. It is absolutely revolutionary compared to what was available.
It's very, very rare in science that you make a big step forward in your measurement capability in the way that JWST has done for astronomy. And it just doesn't happen very often in the history of science, and that's really exciting and significant.
One of the things that makes James Webb so special is its gigantic mirror.
So that there are various things that make the primary mirror on James Webb special and incredible. I mean, the first is the sheer size of the mirror. It's the largest one ever launched.
The Webb mirror is around 6.5 meters in size. So if you can imagine that, that's bigger than most houses that you're walking by.
It's so large it wouldn't fit in the rocket, so they had to devise a way of folding it up so that it would fit inside the top of the rocket.
It's absolutely humongous. And that makes a really big difference in terms of the sensitivity of the telescope.
Well, it's thousands of times more sensitive than Hubble. It's a step forward of factors of 1,000 or more. Factors of several thousand, in fact. I'm correcting myself.
The bigger the mirror, the more light you collect. The bigger the collecting area, the more sensitive you are and the further you can see.
The other thing that makes it absolutely incredible is the precision with which it's been made. If the mirror was stretched to be the size of the United States and you were to measure the size of the biggest bumps and dips on the mirror, you're only looking at a bump or a dip of order 1 centimetre in size. It's absolutely incredible, and that's what generates the near-perfect images from the primary mirror.
But it's not just the mirror that makes the images from James Webb so incredible. It's also the type of light that it detects. The James Webb Space Telescope detects infrared light, which is a wavelength of light that we can't see. But the unique properties of infrared make it incredible for exploration.
So with the infrared light, you can see the atmospheres of exoplanets. There's molecules in star formation regions, things like caffeine and alcohol and water ice, the signatures of life around other planets.
So just a few things then. Infrared opens up the possibilities for astronomers like Olivia and allows them to capture images that would previously be impossible in the optical range. But even within the infrared spectrum, there are multiple different wavelengths. On board Webb, there are 3 instruments that observe near infrared. This is closer to the visible spectrum. But the instrument that's garnering the world's attention is the mid-infrared instrument on board JWST, known as MIRI.
MIRI is essential for JWST. Without it, you can't see the cooler phenomena in the universe. You can't peer back as into the earlier stages of star formation as you would like.
So MIRI is an incredibly significant and important instrument. The image contains far more detail than has ever been done before.
So when we look at it in a new wavelength of light, we find things that we hadn't expected to see, and that's a really important part of how you discover things about the universe.
MIRI allows us to see further along the infrared spectrum, and this in turn allows us to see through dust clouds and further back in time than ever before. That's because as galaxies move away from us, the colour they emit shifts further into the infrared, so the longer the wavelength we can observe, the further back in time we can see. But despite the capabilities of MIRI, it very nearly didn't make it on board James Webb.
So MIRI wasn't initially part of those plans because it seemed technically very complicated, and I think people were thinking about the science in a slightly different way. And so I started making the case that really we needed to add a mid-infrared facility to the telescope.
Gillian Wright is the European Principal Investigator for MIRI and the Director of the UK Astronomy Technology Centre, and was instrumental in pitching to get MIRI on board Webb.
When I found out it was confirmed that MIRI was going to be on board, I remember being very happy and also knowing that I was going to be very busy for a large number of years.
Gillian wasn't wrong. Construction of James Webb Space Telescope started in 2004, and 17 years of work later, on Christmas Day 2021, with MIRI securely on board, the telescope finally launched.
And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
I've been looking forward for the Webb launch for many, many years. And as it got close to Christmas Day, I was extremely nervous. I don't think my family enjoyed Christmas morning with me because I had on the TV the Webb launch playing, and I was quite nervous. I had my pillows ready in case I needed to hide.
Everything went perfectly. It was an incredible launch. It was a pleasure to watch.
So it was a very good Christmas present.
It was a lovely Christmas present, it really was.
Over the next few months, the James Webb Space Telescope travelled over 1.5 million kilometres away from Earth to its new home, gradually turning on the instruments along the way.
So then it was getting really exciting because we've been from Christmas Day all the way through until the late spring when MIRI finally gets turned on.
As the instruments are being turned on, it's both exciting and it's nerve-wracking because you know that there could be things wrong.
After decades of work, the James Webb Space Telescope was finally operational, and it wasn't long before the images started coming in.
I knew when Webb was going to take its first images, they were going to be spectacular. What had not prepared me was just how spectacular they were going to be.
The first images were just incredible, just so beautiful. It was amazing.
And then when the first images came back, I was just absolutely astounded at how good everything performed. And I've been smiling ever since. It's almost emotional.
The images are spectacular. And the only thing more spectacular than the images are the discoveries that lie within them.
So one of the things I think that's really exciting about the early images is the way they show how MIRI really adds information.
I can see details in there that I knew existed, but I never thought I'd be able to see with a scientific instrument. Some of the first Webb images released were of the Southern Ring Nebula. This is a planetary nebula, which is a star at the very end of its life. In the MIRI image, we see actually a second star. So we can see a red star and a white star. So these are actually a binary system, and that's the very first time we've seen this binary companion in the Southern Ring Nebula. This is an image of Stephan's quintet, 5 galaxies that are interacting with each other. And what you can see in this galaxy up here is actually material falling into a black hole in an active galactic nuclei. You can see the material in the galaxy is actually orbiting and falling into the galaxy itself. This is 13 times further than what we've been able to see before in the infrared.
I mean, JWST has already found the furthest galaxies we've ever seen, the highest redshift ones, the closest, and that's only in the first few weeks of operation, and that's really exciting, and I think it's an indication that there's going to be a lot more discoveries to come.
With Webb, we've designed it to answer many of the questions we already know about the universe. But as with all new telescopes, there's a realm of new discoveries.
The mysteries that will arise, I think they're really exciting.
New questions to answer.
The questions we don't know how to ask just now, and I think that's really exciting to see something that not only has nobody ever seen it before, but nobody expected to see it.
I feel very privileged to be part of this.
I'm proud to be part of JWST. It's been an amazing journey and a fantastic privilege, really, to be part of it.
I think it's just incredible. I helped make that instrument, and when I see these images, I'm just full of smiles.
Very first data we got from Parker Solar Probe, for maybe 15 minutes we were thinking there is something wrong with the instrument. Only to realize that no, the instrument is working perfectly, and actually what we are seeing is physics. It's physics that we have not seen before.
The Sun is the most important celestial body in space, at least to us here on Earth. It drives weather, ocean currents, seasons, the climate, and without the Sun's heat and light, life on Earth would not exist. But we don't understand it as well as you might think. That's where Parker Solar Probe comes in, NASA's first ever mission to touch the sun.
It's a voyage of discovery. It's a groundbreaking mission. It is steeped in history.
This is Nicola Fox, the Director of Heliophysics at NASA.
So the concept of Parker Solar Probe has been around for over 60 years. And so, it's been the most high priority science for us to do, but it was always so challenging technically. And then, finally the technology catches up with the scientists' dreams and we're able to really achieve the mission. But nothing about Parker Solar Probe was easy.
Not only has the probe travelled nearly 90 million miles closer to the sun than Earth, but it's had to withstand temperatures of over 1400 degrees Celsius. Keeping it cool is the job of thermal engineer Betsy Cungdon. How hard could it be?
So the task of designing a heat shield for something that's going to the sun is immense. Anytime you're trying to do something that has never been done before, while it is really exciting, it is also very stressful. One of the things when you're designing something for space as an engineer is you actually want to keep things quite simple. The Parker heat shield is about 4.5 inches thick.
Yeah, just 4.5 inches is protecting this probe from thousands of degrees Celsius.
The Parker heat shield is about 4.5 inches thick, and on both sides there is a material called carbon-carbon. It's a lot like the graphite epoxy that you might find in your golf clubs or in a tennis racket. And then in between is carbon foam. And so that together, as basically just a big sandwich, is what protects the probe from the sun. As Parker Solar Probe approaches the sun, and it's in its last approach and closest approach, the front side of the heat shield will be at 1400 degrees Celsius. But the probe itself, the spacecraft, where all the electronics are, will be at room temperature, like in the 20s degrees Celsius. And so it's almost like it doesn't even know it's at the sun, and it can do this amazing science.
So thanks to Betsy and her team, Parker Solar Probe will be travelling closer to the sun than anything before, but remain around the same temperature as the average swimming pool. But there's one more detail that made this historic moment extra nerve-wracking for the scientists. The Parker Solar Probe is fully automated, meaning that once the little probe was fired into space, there'd be nothing the scientists could do to control it. Except
there are these little sensors that are the farthest things that stick out behind the heat shield called solar limb sensors. And they're designed that if they light up, the spacecraft knows that it's going off a little off track a little bit, and it needs to right itself. And so it will right itself without any commanding from Earth. We don't have that kind of time to actually right itself. It has to do all that on its own.
So all they could do was hope. On the 12th of August 2018, after over 60 years of planning, Parker Solar Probe finally launched.
Every single member of the Parker Solar Probe team, when we watched the launch, really felt like we were losing a member of the team.
I worked on Parker Solar Probe for 10 years, and at launch, I cried. It was a very emotional moment. And when I see the launch videos, I still get emotional about it.
There was separation anxiety. There's the feeling that this thing that you've worked on for so long is going to leave and not come back. And really, she is the part of the team that's actually doing the exploration.
Parker Solar Probe has had one extra helper out in space though, Venus. Rather than flying in a straight line towards the sun, Parker Solar Probe uses the gravity of Venus as a giant slingshot, catapulting it into closer and closer orbits of the sun.
The first Venus flyby, I think, was the really key one for everybody. Once that maneuver was done, we were go for the sun at that point.
The first solar pass was really emotional but amazing. Of course, when it was actually in the solar pass,
then that's terror.
We can't actually talk to the probe while it's going in. So
until the spacecraft came back out from the other side of the sun and everything was healthy.
When you get that green beacon that everything is looking good after a solar pass, it is just an amazing feeling.
My God, we've done it.
So after having launched Parker towards the sun, on its 8th flyby in April of 2021, Parker Solar Probe finally entered the atmosphere of the sun.
It reminds me of 1969. Every time I see the movie when Neil Armstrong touches the surface of the moon.
It's one small step for man.
That was monumental. In a way, it's a parallel to Parker Solar Probe. When you fly through the solar corona for the very first time, nobody has done that before. It was so exciting and also so humbling to have launched this mission, throw it basically toward the sun, and returns you some data that you never seen the like of it before. It's just eye-opening.
Noor Rawoufi has been working on Parker Solar Probe for over 14 years. And in case you're wondering if he still enjoyed it,
it's better by the day.
But the thing that's been exciting Noor more than anything before is the incredible discoveries coming from Parker Solar Probe.
The amount of discoveries, it's way beyond any of us could have imagined. It's just mind-boggling. We are discovering by the day new phenomena in the data that Parker Solar Probe is sending us. Well, the very first data we got from Parker Solar Probe, when we got this data from the fields instrument, we were looking at the magnetic field measurements, and for maybe 15 minutes we were thinking there is something wrong with the instrument. Only to realize that no, the instrument is working perfectly, and actually what we are seeing is physics. It's physics that we have not seen before. And it is these switchbacks, basically the magnetic field will flip over itself, making a rotation of 180 degrees and out again. And it does that in a matter of seconds to minutes, and it is just fascinating. What is really important about these switchbacks is that they carry a lot of energy with them. And that energy will dissipate it into the solar wind in the form of heat and speed. Two of the three goals of the mission is to explain the coronal heating and the acceleration of the solar wind. So the switchbacks could be the smoking gun that actually leads to give us the answer to those questions.
By understanding switchbacks, we could unlock the secrets of solar wind and how it's formed and accelerated towards Earth. Solar wind is not trivial. It reaches speeds of over 1 million miles per hour, travelling way beyond Pluto, and it affects our everyday lives. In 1989, a large solar flare caused the entire grid of Quebec, Canada to fail, leaving them without power for over 12 hours. So think what it could do to a rocket or a satellite. And as well as solving mysteries, Parker Solar Probe is also creating puzzles for Noor and his team to try and solve.
Parker Solar Probe, like any other missions, and answer questions, but by answering a question, it actually poses many more other questions. In a way, that's the essence of exploration. We come to this world as explorer, and we leave it as explorer. On the eve of Christmas of 2024, we will reach the closest approach to the sun ever. That will be 3.8 million miles from the solar surface. It's so close to it. And after that, we do 2 more orbits, and that's the end of the Prime mission.
But even after this mission ends, the discoveries made during this epic mission will live on forever in the science and in the scientists.
It is the highlight of my career, and it will be the highlight of my career. Definitely being involved in Parker Solar Probe, it's an honor.
We are really rewriting the textbooks about the sun, and it's amazing to have played a small part in that.
I am incredibly proud to have been part of the Parker Solar Probe mission.
Parker Solar Probe changed me forever. Parker Solar Probe is an enabler in many respects. It emboldened us now to go after very challenging ideas and concepts for future missions. So we are not stopping here.
Right now, the 2 Voyager spacecrafts are hurtling through interstellar space at 35,000 miles an hour. The space is so far away that it took 35 years to get there. And now we need new science to understand it.
I couldn't believe how nature was fooling us.
It made us rethink everything we knew about the shape of our solar system.
I think I discovered that the tail has a croissant shape.
And even where the edge of our solar system actually is.
There was a lot of confusion. Actually, the confusion lasted almost a year.
Even just to understand what Voyager is trying to say requires a very special set of skills.
It's really like a Swiss watchmaker. It needs to be a trained eye to tell me, can I trust this data or not?
What's even more extraordinary is how Voyager, the old spacecraft from 1977 with 64 kilobytes of memory, was able to make this journey at all.
3, 2, 1. We have ignition. and we have liftoff.
Both Voyager 1 and Voyager 2 were launched in 1977, and it had to be then, thanks to an extremely rare planetary alignment that happens once every 175 years.
Where we could fly past Jupiter, get a gravity kick and go to Saturn, get a gravity kick and get to Uranus, and another gravity kick and go past Neptune.
Within just 2 years, Voyager 1 had reached Jupiter. Voyager showed us a planet, which looked so serene through a telescope, was actually rocked by hundreds of raging hurricanes, a glowing aurora at the North Pole, and 3 thin rings. Voyager took 33,000 images of Jupiter and its major moons that captured the world.
And we'd get to see these pictures and go, whoa, look at that, what's going on? It was fantastic.
On a night like tonight, our eyes, our minds, our souls, our blood are moving out through the universe. We're part of history, and that means that we have to replace the old myths with new ones.
Just 1 year later, and Voyager 1 had already sped past Saturn, spying intricate details in the planet's rings. From Earth, scientists could only see 5 or 6 of Saturn's rings. Voyager showed us that there were more than 100.
And I can remember those first pictures as we flew away, looking back at that system and seeing the reflected sunlight in that structured ring system was just so beautiful.
Then the Voyagers parted ways. Voyager 1 headed straight for the edge of our solar system. Voyager 2 took a more scenic route, reaching Uranus in 1986, and eventually Neptune in 1989, showing us yet more outstanding views of the green and blue planets, and spotted geysers on Neptune's large moon, Triton. And that was the main mission, the first human-made object to reach the distant worlds of our solar system. But the Voyagers weren't done yet. They were about to embark on the journey to search for the edge of our solar system. And before they left, there was one last thing to do.
Carl Sagan convinced NASA to turn the cameras towards Earth and take that very famous picture, the pale blue dot.
On that blue dot, that's where everyone you know and everyone you ever heard of and every human being who ever lived out their lives. It's a very small stage in a great cosmic arena.
These images were the last of 67,000 images taken by the 2 Voyager spacecrafts. Their cameras were then turned off to save power as they carried on their journey towards interstellar space, the boundary where our sun's solar wind ends and the rest of our universe begins. Problem was, nobody actually knew where it really was. Scientists thought that sooner or later, the charged particles that create solar wind were going to run out, and Voyager would enter a pristine environment of interstellar space.
We thought that would happen, maybe just beyond Neptune. But no, that didn't happen. Well, we said to NASA, give us a bit more money, another 5 years. Well, this kept happening year after year. NASA, please give us a little bit more money, a little bit longer, soon we'll be there.
As Voyagers 1 and 2 continued to move out into the outer reaches of the solar system, they remarkably continued to send very faint signals back to Earth.
And this is what makes it so interesting and so fragile. The whole instrumentation of Voyager was designed to visit the outer planets that have very strong magnetic fields. So now you're dealing with a signal that is almost at the noise of the instrument. And because Voyager was not designed for that, it's a miracle fit that all this team is able to go mine the data and pull out the signal and tell us what's going on.
Just 5 instruments were still operating on the spacecraft, and in 2012, more than 35 years since Voyager 1 left Earth, scientists started to see the first signs that they were crossing into interstellar space, through the boundary known as the heliopause.
Think about the heliopause as your walls of your house. This is what separates the environment that is dominated by the solar wind from environment that is dominated from other winds from other stars outside of our bubble, the heliosphere.
The expectation was that there would be a sudden shock, a burst of activity that would make it obvious we had finally reached this sharp boundary. But the reality was much stranger. All of the detectors on Voyager were seeing particles suddenly appear, and then disappear, then appear and then disappear, and nobody had a clue why. these strange particles seem to be coming from elsewhere in the galaxy.
Did we cross or not? The data was so confusing.
On one hand, Voyager was still being affected by the sun's magnetic field, but the particles were suggesting we had crossed.
It turns out what really tipped the scale in the team was the radio data.
The data was stored on the spacecraft using a tape recorder. So ancient technology, it's extraordinary. But it worked. And the data were gathered and sent back bit by bit.
And 6 months later, we turned to the radio station of Voyager, and guess what we heard?
These plasma waves, converted into sound that we can hear, were the final proof that we had crossed the boundary into interstellar space.
The first human-made object to venture into interstellar space.
Even more extraordinary than crossing the boundary into interstellar space was what the data said about the shape of the solar system.
I was tasked to create a computer model with all the physics that we know to kind of predict this shape of the heliosphere.
It turned out that the solar system's heliosphere is not round like you'd think. It has a tail from whizzing around the galaxy. And more than that,
I was finding that it has a croissant shape, 2 horns with a void in the middle. It was just a shock to realize that something such basic as the shape of our home is completely different.
And all of this was discovered by a small, extremely low-tech probe more than 10 billion miles away. And they're still going. In 2018, NASA's Voyager 2 spacecraft crossed the boundary. Finally, both Voyager spacecrafts, with their 1970s technology, had reached where no human-made object had ever been before: interstellar space.
There's very little material, very empty. Space can be very, very empty.
The environment out there is colder and denser. And of course, it's dark. There's not a lot of light. You're far away from the sun.
Voyager has also discovered that our solar system's impact is much bigger than we thought before.
We would have liked to get to a region where the heliosphere doesn't influence anymore the interstellar medium, what we call a pristine interstellar medium. What we're measuring now is a medium highly disturbed by the sun.
The Voyagers are still sending us ever fainter signals, still teaching us new things about interstellar space, but they're running out of time.
We probably have 2, 3, maybe 4 more years of power to communicate with Voyager.
But there are still so many mysteries left to be solved.
What is the environment outside? What's happening in the nearby stars that are influencing our system and so on?
So one of the beauties of the Voyager mission, that it started as a planetary mission, gave us the first images of our planets, discover volcanoes in the solar system, and then it went to discover our heliosphere, our vast, regions of our solar system, and enter into the galaxy.
Long after their power has gone, the Voyagers will continue to rush away from us, monuments to human endeavour and exploration, heading out towards the stars.
Voyager will continue its little journey in the interstellar space, way past when we maybe as a species will cease to exist, when we might move to a different planet.
It'll keep going and going and going and going and going forever.
We're used to seeing NASA fire up its rockets and launch billions of dollars of equipment into space. But what happens when it messes up?
The Hubble Space Telescope project has suffered yet another setback.
And how do you fix a $1 billion mistake up in space?
I did not have a line item that says NASA put wrong mirror in telescope.
With engineers needing to fix it not once, but twice.
So the summer 2021 event was a pretty intense anomaly.
This is the story of how the Hubble Space Telescope nearly destroyed NASA's reputation, and the retired engineer that helped bring the telescope back from the brink both times.
When I received the call, I was honored that they would think of me to try and help them resolve this.
This is electrical engineer Ron Barish.
I started working on Hubble in 1987, approximately 2 years before launch.
Hubble was one of the most ambitious space projects the world had ever seen. NASA had spent hundreds of millions designing a massive mirror in the telescope to get the sharpest pictures of the universe ever seen. Expectations were high. It promised to catapult space science into a radical new era, and all eyes were on it.
And liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
It was very exciting to watch the launch. When it was turned on in orbit, very exciting.
NASA was quick to champion it as the greatest advance in astronomy since Galileo. But then disaster struck.
The Hubble Space Telescope project has suffered yet another setback. Engineers have discovered that the giant telescope has a warped mirror, which means the images sent back to NASA are distorted. The pictures are little better than those from ground-based telescopes.
We found out that there was distortion in the image. Well, the images I saw were blurry. They called it spherical aberration.
When light enters the telescope, it's reflected first by a large 8-foot mirror, onto a smaller secondary mirror, which concentrates the light onto the cameras. If either mirror is slightly out of true, the picture becomes distorted.
And that's exactly what had happened. The mirror hadn't been tested with the rest of Hubble. Had it been tested, the scientists will have seen that the mirror was ground incorrectly by just 1/50th of a human hair. Tiny, but enough to ruin everything.
Everyone on the project was very disappointed, and it was an embarrassment that we had spent so much time on the program and that there was a significant flaw. The news was not very kind to the project.
For the American taxpayer, they're not going to be happy.
Well, look, you launched this $2 billion white elephant. What are you going to do?
And the bad news kept coming, as NASA's reputation received blow after blow after blow. But despite the setback, there were still some that had hope for Hubble.
So do not write off the Hubble telescope. It merely means it's not going to be quite so good as expected until the repairs are carried out.
Replacing the mirror wasn't practical. So instead, Ron and the rest of the team created an instrument called CoStar, which would act almost like a pair of glasses, redirecting the light to account for the flaw in the mirror.
My job was to provide an electronics interface box called the Remote Interface Unit, CoStar.
3 years after Hubble's embarrassing start, they finally had the parts needed to fix the broken Hubble Space Telescope. All that was needed now was a team of astronauts bold enough and daring enough to attempt a mission of this magnitude.
There weren't very many of us in the office at that time who had done spacewalks, and so that's how I got kind of a quick turnaround from one flight to the next.
You know, in all the failures, the hundreds and hundreds of failures I came up with that I had to accommodate, I did not have a line item that says NASA put wrong mirror in telescope.
Catherine Thornton and Story Musgrave were two of the astronauts that were selected for the mission, and in 1993, they set off. The world held its breath as the astronauts carried out 5 back-to-back spacewalks in an attempt to bring Hubble back from the brink.
The first spacewalk on Hubble, did the dance. When the music starts, what you gonna do? Well, you got a power tool and you unbolt the thing, you undo the connection, zip, zip, stick it in the box. Hang it over there, get the new one out. Slide the new one in. It's fingertips, baby, fingertips.
That's what's so awesome about Hubble. It's almost like plug and play. We installed CoStar. We installed a coprocessor on the computer to give it more memory, added a new magnetometer, and other cats and dogs, as we called it.
It is easy. You've got to make it easy.
Around the world, astronomers anxiously awaited the first pictures from Hubble's new camera. On the 18th of December, 1993, the results came in.
Hey! Right there! Oh! Get it!
When an image hit the monitor, the whole room, everyone screamed. It just got it fixed.
Okay.
That is better than any deconvolution you've ever seen.
Yeah. Those are actually stars.
I think you got it. Yep, sir. Maybe a little premature, but I'll shake your hand.
When the images first came back and I saw them, made me feel proud that I was part of that mission and that we had brought the telescope back to what it was supposed to be. As a matter of fact, my understanding is the images were clearer than what they had ever expected.
To the relief of Ron, NASA and the entire world, Hubble was finally fixed, and it immediately began to deliver on its original promise, allowing us to see the universe in ways we could previously only dream about. Hubble was only supposed to last 15 years. Instead, it continued to make groundbreaking discoveries for more than 30. But then in 2021, it suddenly shut down. And the team at NASA once again had to fight for Hubble's survival.
So the summer 2021 event was a pretty intense anomaly, probably one of the more dramatic ones that we've had.
Nzinga Toll is the anomaly response manager for Hubble, and it was her job to figure out why Hubble's computer had shut down and ultimately find a way to get it back up and running. But that was far easier said than done. So Nzinga had to think outside the box.
After the first few days, and it wasn't immediately apparent that we could get a path forward to resume science, we knew we'd have to pull in a lot more folks.
With Hubble still showing no signs of life, Nzinga knew she needed some very niche expertise to try and help fix Hubble. So she called upon Hubble's original architects to come back and get stuck in.
When I received the call, I was honored that they would think of me to try and help them resolve this. Anytime you work on a system like this, it's part of you. It's if there's ever a problem with a spacecraft in orbit, everyone jumps in and works on it, even if you're retired. A lot of people were concerned that we would not be able to fix the Hubble. It was very stressful. The last thing I wanted was to have the system that I spent 18 years of my life on to be the cause of the end of the mission. And so I was under a lot of stress.
But undeterred by the challenge, the team set to work to identify what went wrong and get Hubble back online.
The telescope was down for approximately 4 weeks.
I think the first couple of weeks was probably the most frustrating and the most anxiety producing.
We put together what's known as a fishbone diagram. Everything that could possibly cause the problem was written down, and we eliminated them one by one until we zeroed in on the exact cause. It was amazing how everything came back to me.
On July 15th, Nzinga and her team successfully powered up the backup computer on board Hubble, and over the next few days, the team gradually brought the science instruments back online.
Once we realized that we had solved the problem and the telescope was back up and running, it was quite a relief.
Mainly relief. Mainly a lot of relief.
How did it feel compared to 93?
In my case, it was even better. This was my system that had stopped, that had halted the telescope, and to be able to get it back up and running was very proud. I was very proud when, after the first servicing mission, that we got the telescope up and running, but this was more personal. If another problem comes up, I'd be very proud to work with this team again to resolve any future issues.
It would be an honor and a privilege for me to be called back to support Hubble at any point in time. I will always be a Hubble hugger.
We've waited years for this. I waited years.
This was almost the perfect day. Almost.
Rosetta was and is a unique space mission.
It's a travel not just in space, it's also a travel back in time to the very early days of the solar system.
This is the story of the epic, ambitious mission to land a spacecraft on a comet hurtling through space. Nothing like it had ever been attempted before or since.
Rosetta completely transformed our view of comets.
It was a mission 25 years in the making that all came down to a few frantic hours.
Philae was not anchored.
It bounced. We don't know where it is.
But let's go back a bit to 2004. The Rosetta spacecraft, with its little Philae lander tucked away inside, is about to launch.
3, 2, unité. Top, allumage EAP, décollage.
Well, the actual launch took place on 2nd of March in 2004.
The first part of the mission was just to catch up with the mysterious comet, known as 67P. That took 10 years, during which time everything on board Rosetta was powered down, only to be woken up as it neared the comet.
It was quite a nervous time when Rosetta was coming out of hibernation.
Because if it didn't wake up, that was curtains, really.
€1 billion of kit out in space, and if it didn't call home at the expected time, there was very little that could be done about it.
And then it got this signal, wake up Rosetta, and it's just like, hasn't woken up. All right, send the signal again. Switch it off and switch it on again. Ta-da! It's woken up, which was just so much of a relief.
Hurdle 1 out the way.
When Rosetta woke up, that was really the point where everybody got excited again. We had no idea how the comet would look like.
We don't know what shape it is. It's probably spherical-ish.
We didn't immediately see the high quality images. We saw better and better ones the closer and closer Rosetta came.
Then, wow, what shape is that?
The shape is not potato-shaped as we expected, not roundish. It's
The comet has this kind of rubber duck shape.
It's like one of those yellow plastic ducks.
And that made Hurdle 2 that extra bit harder, landing Philae safely on top of it.
There was no area on this comet which is nice and smooth as we have hoped for. The terrain was rough everywhere. So there was a risk, but that also made it fascinating and interesting.
Philae was equipped with little harpoons to fire off to help it cling to the comet once it made contact. And the landing site had to be meticulously chosen to allow Philae to recharge its solar batteries in the glow of the sun. The stakes were huge. This was a lifetime's work for most of the scientists on the Rosetta mission. The team already knew there may be a problem with the thrusters that were supposed to slow down Philae's approach, but the time had come to deploy Philae. And on the 12th of November 2014, off it went.
One could see the Philae lander as it moves away from the main spacecraft, getting smaller and smaller with the landing gear successfully deployed. I found this already very emotional to see the baby go after 10 years attached to the spacecraft. You now see it in freedom on its way the last 22 kilometers to the surface of the comet. And then Philae was free falling for almost exactly 7 hours to the surface of the comet.
Everybody was, jittery and just waiting and waiting and waiting for the signal to say it had landed.
And then
I just went absolutely, hey, it's landed, I'm so excited, it's landed. It was just the tension that had wound up and the release of that tension and the relief.
We've waited years for this.
I waited years. I'm just so excited. I'm gonna cry. I'm sorry. It's fantastic.
And of course, everywhere in the world, in the control rooms, in the scientific teams, people started to open the champagne and started to celebrate.
It landed. It was fantastic. It was wonderful. Everybody was really, really, really happy.
In the control room, we thought, yeah, great, we are landed. We have the touchdown signal.
But the mood in the control room was suddenly very different. Something wasn't quite right.
Within a few minutes, we realized that although we have landed and although we still got radio contact, which was positive, we did not anchor and the lander was moving again.
And then the principal investigators came out of their little cocoon, and Ian came up to me and he gave me a big hug, and I gave him a big hug, and I said, oh, you know, it's fantastic, isn't it? It's really great, you know, you must be so proud and pleased. And he said, no, it has gone wrong. It bounced. We don't know where it is. I said, what do you mean? He said, well, it hasn't been announced yet, but it will be announced in a minute that actually Philae did land, but the harpoon didn't anchor it, and the little crampons on the legs couldn't get a grip, and so it's bounced.
And we had no idea what's going on, where we would jump and how we would land and when we would land.
Oh dear.
Philae had crashed off the face of the comet and bounced about 1 kilometre back into space. Any further, and it risked escaping the comet's weak gravitational pull and drifting off into space forever. Anxiously, they waited.
We had no idea whether this would be a successful mission or would be just a touch and we would never again hear from the landers.
And then the news came in.
So we did land somewhere, and we still had radio contact. We still received signals, and this was the moment of great relief, because that was the moment where we knew we are at the surface and we can still communicate with the lander.
But the good news didn't last long. It had landed in the shade. Not great for something reliant on solar power. This meant they had less than 72 hours of battery time to undertake months' worth of scientific collection. The clock was ticking.
So it's one of those things, it's like, okay, let's just throw away 10 years worth of calculations and let's just redo them all over the space of 5 hours, which is what they did.
We also optimized the sequence in a way to get the maximum science out of the energy available.
Once they knew they'd only got 70 hours, and it was just going to seep away, it's like it wasn't if you turned all the instruments off, the battery would stay at that particular level. No, because it was so cold, it was having to maintain, it was having to keep heaters on as well, you know, to make sure that the instruments kept working. So you just knew you'd got 70 hours full stop, all right? So you worked for 70 hours. You just did it. You just barreled through, get as much data as we can.
And amazingly, almost all of the instruments on Philae had survived the impact. It was go time.
We were very lucky. I mean, we ended up in an orientation that the antennae were pointing, upward, so to say, that we could establish a radio link with the main spacecraft. And again, we were also lucky because we could switch on the instruments. We could do fantastic science from the surface of the comet.
About 80% of the science goals of the Philae lander were achieved. So it was an absolute fantastic success. You know, the fact it crash landed, got around that. It was an amazing success.
This was, of course, a bit sad to see the voltage of the battery drop and knowing that Philae will go into a hibernation.
And eventually, that's what happened. But even in those few hours, Philae had unveiled a world full of surprises. Of dust and debris, gases erupted from deep within the comet. Even the crash landing threw up interesting discoveries.
Even by analyzing the bounce itself, we got information on what's the surface made of. And it was a bit surprising that the surface was rather hard.
But perhaps most exciting of all was what this comet was able to teach us about us.
The Rosetta mission had as one of its goals to understand the building blocks of life.
Because Comet 67P was rich in organic compounds like phosphorus, carbon, oxygen, nitrogen, and the amino acid glycine, all essential for the origins of life, and offering tantalizing clues as to how these compounds may have arrived on Earth in the first place.
So the original building blocks of life came from comets.
While Philae had gone into eternal hibernation, the mothership Rosetta continued to fly around the comet, collecting data for 2 more years. But then, Rosetta's time had to come. In a last-ditch effort to get as much out of the mission as possible, the team decided to crash land Rosetta into the comet, collecting data along the way and allowing the scientists to get one last look at their old friend Philae.
Took this sort of shallow dive onto the surface of the comet and then sort of crash landed, and its camera was going the whole time. So we saw these last pictures of the surface rushing up to greet Rosetta. And then the signal died, and you got this little sort of oscilloscope thing with nothing on it. Just like, you know, like somebody when they die and you see the signal die on the heart thing. And it was just like, it was so devastating. People were in tears, I cried. And it's just, hell's teeth, it's a robot, you know. But it's been part of your life for so long and so important. So that was it. That was the end of the Rosetta mission.
There is still many publications done using the data from Rosetta. That's still the most relevant and best scientific information we have from a comet.
Rosetta completely transformed our view of comets.
To some extent, what we know about the evolution of the solar system and what we believe about the formation of life, all of this is triggered by Rosetta, and this is not often in lifetime you get a chance to get involved in such a project.